In this problem, we're asked to make various approximations of a function for which we are given select values of the function and its derivative at various values of the input variable. And the first part of the question is to find a first-degree Taylor polynomial about x equals 2. And so we're going to write that we're going to call the first degree approximation p1 of x. It equals the value of the function at 2 plus the first derivative of the function at 2 times the distance away from 2. And so in this case, what we have is given as 80 plus 128 times x minus 2. Now, to evaluate that at x equals 1.9, it's just 80 plus 128 times 1.9 minus 2. That gives negative 0.1 there. And so what we're really talking about here is negative 12.8. And when that's added to 80, we end up with 67.2. In part B, we're simply expanding this approximation to be the third degree Taylor polynomial. And we're repeating the exercise from part A. So we will write that P3 of x is equal to 80 plus h prime at 2, which is given as 128, times x minus 2, plus the second derivative, namely 488 over 3, times x minus 2 to the second power, and that over 2 factorial. And then there's a final term, plus 448 over 3 times x minus 3 cubed over 3 factorial. When we plug in 1.9 into this, we have 80 plus negative 12.8. This we're just copying over from the previous part A. And then we've got some additional terms, namely we have 488 over 3 and that's going to be times 0.01, the result of taking 1.9 minus 2, which is negative 0.1, and squaring it. And that's over 2 factorial. And then finally we have 448 over 3 times negative 0.01. 0.001. This is just negative 0.1 cubed. And that is over 3 factorial. Well, when you do all of those calculations on your calculator, you come up with an approximate value of 67.98844. So part C asks us to find the error, or rather, it asks us to show that the error of H1.9 is less than a certain value. So let's just recall that the whole concept of the Lagrange error bound comes from the fact that you can always describe a Taylor series expansion over the range for which it's well defined, for which it converges, as the sum of the first n terms, and in this case I'll just leave a few out till we get to the third term, H3 at 2. I made a mistake here. I'm going to fix that. It wasn't at 0. It was H at 2. Okay, so this is the first degree term, the x minus 2 to the 1 power, then the x minus 2 to the 2 power. I've just elided over those because they've been written before. And then we know that we have the x minus 2 cubed over 3 factorial. And then we have a remainder term. And what we're told is that just going to partition off this much of the answer space. What we know is that the remainder term is equal to the fourth derivative at some value between the point where we're expanding the series about and the point that we're measuring. So in this case, somewhere between 1.9 and 2, and then at x minus 2 to the 4th power over 4 factorial. Furthermore, we know that that value is less than or equal to the fourth derivative at some point, we'll call it C max, that gives us the highest value of the fourth derivative over that interval between 1.9 and 2 times x minus 2 to the 4th over 4 factorial. So the question really is, where is this C max? Where is the fourth derivative in that interval between 1.9 and 2? Where is it largest? Well, we're told that all of these derivatives are increasing as we go from 1 to 3. So we know that the largest value is right at 2. And so that means that this value equals H4 at 2. And here all along we've been interested in this evaluated at x equals 1.9. 1.9, 1.9. So now I'm going to actually plug in the 1.9. And that gives a negative 0.1 to the 4th over 4 factorial. When you plug in what you have from this table over here, namely the fourth derivative right at x equals 2, you get a number, namely 2.6 70370 times 10 to the negative 4. And that number is decidedly less than the bound that we were asked to prove it for, namely 3 times 10 to the negative 4. So we have shown that the Lagrange error bound gives us a worst case error that is certainly less than 3 times 10 to the negative 4.